a long time and see we try to face this. So indeed, I'll tell you something today I've been working on for what I call an academic project with Loga and various people on trying to understand open quantum systems from holography. And what I'm primarily trying to do is summarize what we've learned in the last 2.5 years, which should appear in a paper tomorrow with Loga and our postdoc Loretta. And along the way, I'll mention what were the sort of ingredients that went into this. Okay, so I have three broad motivations for this. I'm just going to say it in words, right? So one of the things that drove us to thinking about this problem was to basically understand the real-time response functions, but also the associated quantum stochastic fluctuations of black holes from a perspective that's intrinsically Lorentzian, not a Euclidean perspective, which we very well understand and have been very instrumental in making progress at various contexts in the path of quantum gravity. So the elements of the Lorentzian quantum gravity path we understand very well. I talked to you guys about this 2 years ago, but that won't be what the focus here. I'll use a particular example to illustrate features of the Lorentzian path integral techniques. At least at the saddle point level, that implies some interesting things that follow. The second, which is something close to my heart, is to use this to derive effective field theories for hydrodynamics, especially in systems with long-lived gapless modes, which are emergent at low energy. So again, we know there's a connection between hydrodynamics and gravity going back decades, for Polycastro clarinets, the areas level, and then Fas, Charles, Anthony, extended that to the nonlinear state. But that was the level of response function, that was the level of just the dissipative part. It didn't account for stochastic Hawking fluctuations around. Okay, so there is a story there that needs to be told, which is how does the geometry account for the fluctuations around this fluid dynamical system, especially when these fluctuations are long-lived and have impact at arbitrary length scales.
Sorry to interrupt, but just to understand. But just to understand, I mean, I would have thought starting from the beautiful fluid mechanics picture you want to present, the Hawking evaporation would be some overhead small correction, right? And okay, maybe over time, over the entire half of the over page time or something, it builds up. I don't know.
Yeah.
But otherwise, it might be small. But when you say long-lived, you mean extra beyond hydrodynamical modes, extra long?
Yeah, they're not technically hydrodynamical in the sense that they are the modes that are hydrodynamical 2-point functions, which lead to the dissipation. They're the retarded response.
Mm-hmm.
There's an associated fluctuation piece, which is necessarily there, thanks to the fluctuation dissipation theory.
Okay. Fluctuations in various, either field theory more.
Just the field theory, but they have to come out in the bulk from Hawking process, and you'd like to understand where they come out from and show that the hydrodynamic correlators we derive satisfy fluctuation dissipation.
I see. So these would be, just to understand, fluctuations in correlators of the stress.
Exactly. So anti-commutators are not the return. So as Sandeep says, there will be 1/n. But so you can amplify them, as Sandeep also said, in certain contexts, or you can look at states where they are involved.
And the 1/n², I'm just thinking of as the law of larger.
Exactly. Yeah, because fluctuations are suppressed exactly as they are in sort of real system by other matters. Aspect. And again, this problem at the level of fluid dynamics has been understood again in the last 5-6 years with work that I did with Loga and my former student Felix Hall, and work that you did with Glorioso and Crossley, and Christian Jensen, Amos Jarom, Inzani Fokipa, and so on. So there is a lot of work that did start with gravity. It started with some general principles of Schindler-Keldysh path integrals and KMS symmetry, and derived effective field theory of fluids. We'd like to eventually connect up with that from this discussion. But the thing that I want to focus on.
Mukund, can I ask? Yeah. So the so presumably this is related to the 1/n. So presumably, if you take NF species of bath fields, then presumably you can make it NF over N, and taking a suitable limit, maybe you can, make the effect more.
So there's only one stress tensor operator in the field theory, even if you have many flavors. So the fluctuations in the stress tensor are governed by whatever is the largest parameter, which is 1 over N.
If you're thinking of integrating out the bath fields, then
I haven't told you what my bath is, so wait for it.
okay, all right.
My bath is not what you think it is. My bath is going to program. It's black hole. It doesn't have many fields. It is the largest system.
Oh, okay, all right. Yeah.
And the third part, which is what I will focus on, is basically applications of all this logic to studying open quantum systems. So think of a system coupled to an external environment. Let's say we have some density operator, which is a joint environment, which is and system that I'm going to call P. So this guy evolves unitarily. Gautam, just tell me if this is too small.
No, this is good. Thanks.
By joint a unitary that acts on system and environment. But if I trace out the environment and just look at the dynamics on just the system, the reduced operator on the system, this no longer evolves unitarily, it evolves through some quantum channel, which depends on the environment. But this is just some positive trace preserving operation. It's not necessarily lossy. And the kind of things you would like to keep track of are what is happening to this lossy physics of this quantum channel and what are the fluctuations of this quantum channel. Okay. We're going to amplify those fluctuations. They're going to be not necessarily quantum, they're going to be stochastic, because the small parameter in our game is going to be beta h bar omega. Quantum fluctuations are just as it can be equivalently thought of as stochastic fluctuations at small beta for large temperature. Okay, so we'd like to derive this from a holographic system, but the language for doing this is of course old. And what you would say at a particular level is if you have the system variables and you have the environment variables. So let's say X are environment variables and psi are system variables. I should really write a path integral, which is not just a single copy. I should write something for a density operator. This density operator, for example, is just factorized. Okay, so I can take the environment to be and initially, and the system to be the probe system to be some pure state, like the vacuum state. And then just watch the evolution as time progresses. So if you trace out the system, you basically integrate over the environment variables. What you end up with, if you keep track of both the graphs and the gets, is a path integral on your system, which is double in terms of degrees of freedom, because you have to keep separate track of graphs and gets. And famously, the fact that there was a environmental coupling shows up in the fact that the graphs and gets are no longer uncorrelated. The original action for the probe system was split. And that's this factorized part. But the environmental influence gives you this influence space of finite Vernon, which couples the graph and gets. And the underlying microscopic unitary evolution constrains what terms are allowed in the club. This influence space tells you that influence space came from integrating out something, and therefore the arbitrary things here would violate microscopic.
A question about the earlier part, sorry. Yeah. We know that in hydrodynamics, at least in gravity, the analytic structure of, let's say, a 2-point function is that it has poles on the complex plane and omega.
Yeah.
Now, if you take 1 over n squared account, effects into account, will that somehow smear out these poles?
Well, the poles don't smear out and so if you take 1 over n squared effects into account, there are two kinds of 1 over n squared effects. So there are loop corrections on the retarded correlators, but there are also the fluctuations which go hand in hand by this KMS conditions with the retarded correlators.
Yes.
We are only going to focus on the latter, not on the 1 over loop corrections of the retarded correlators. It's possible that in 1 over n perturbation theory, which include bulk loop effects, there is some smearing order.
Because the particle can break up into two.
Yes, because you have multi traces that can.
Has anyone done a calculation of what that would do to the analytic structure?
Not that I know of. In principle, it can be done, but nobody has done any higher point calculation to what I'm going to.
Just to understand Shiraz's and this exchange, Shiraz, you're saying, for example, I don't know how to do this, but roughly, if you try to quantize fluid mechanics itself, you might have loops.
Yes, and I was thinking in the context of gravity, which is very common. Yeah. You've got, a 2-point function comes by exchanging classically something from boundary to boundary. And because it's classical exchange, there is a pole, definitely. Now, but the guy that's being exchanged at 1 over n can split up into 2 particles. So had it been real particle exchange, that would have taken a pole and made it a current. Now, this is a pole of the imaginary axis, and I'm a bit confused about whether that's the same thing there.
Well, in perturbation theory, in weakly coupled field theories, there are only cons. There are only cons.
Yes.
So actually, it might should something like that should happen.
Yeah.
The reason I said that nobody's done the calculation is we naively think in the way people think of the black hole and the thermal state or thermophile double. Then you have a problem of where do you integrate the vertices of the loop pole. Right. So that's what we're going to fix. That's right.
Yeah.
So that's why the calculation.
Yeah. And just to say, the thing that confuses me a little bit is that sometimes a pole of the real axis becomes a cut by going off into the imaginary plane.
Yes.
This was already in the imaginary plane, so this is why it was confusing me a little bit.
Not clear it will happen.
Yeah, it wasn't totally sure.
Yeah. I mean, I think that will work at the level of 3 levels. We have done loop.
What did you say about not being able to integrate the vertices?
You wait for 30 minutes.
Oh, okay.
I mean, you should not integrate over the eternal black hole. Promise.
You should not be. I thought you'd just take that as a background and do Shiraz's calculation.
Where do you do Witten diagrams? Witten diagrams, when you have vertices, require bulk integration.
Yes. I thought you didn't stop it.
Why?
I don't know. Time is there as well.
It doesn't. So I mean, the field here of intuition, and there is the prescription of this.
Okay, no, not to take away. I was just saying that would be my guess.
One thinks of some sort of scattering process in this open system. What are the different, what physical principle changes? It's because the practical fragments. The unitarity constraints, usually partial unitarity, etc. Those will get modified.
They will get modified. This is not where. So what the way people usually deal with this in quantum mechanics is they posit a particular. They assume a certain structure for the environment. They assume the environment is reasonably has only fast mode, so they can do kind of open hammer. And in that regime, they assume a particular form for this non-unitary evolution. Okay, so let's take a Hamiltonian piece and then they'll add something for what's called invariance. And it's Markovian approximation. You can do something of this kind. We don't want to start with an assumption, especially when we have long-lived gapless. And we'd like to derive what constraints we get in context of gas and control. So, which is why my answer to Gautam was I'm not going to study standard environments. I'm going to study environments which a priori are well behaved for answering this question. My environment is going to be a holographic.
Yeah, but just about Abhijit's question, I mean, the first thing I would say is that an S matrix probably generically becomes indefinite. Because the particle could disappear into the environment. Yes. So it could develop like that. Yeah.
But you that you might have said for resonant scattering, that when you have other kind of thing where the particle does disappear into the background.
Right.
Yes, so you must go on your work on the same mass. Should I think of the environment as a black hole?
That's what we did, but wait for it.
Oh, okay.
Yeah. So let me set up the problem. So the problem is I'm going to take my environment to be a holographic black hole. So let's be concrete. I'll just take it to be n equal to p means, which I'm not as bottom-up models. And let's just couple this to some system, let's just take it to a free field. And was it a linear coupling between this guy and some single trace operator of n equals 4 of some dimension there. So what we want to do here is, in contrast to what most people want to do in the context of islands, integrate out the n equals 4 field. And we want to write down the effective field theory of this single scalar field psi. It's very clear, as put this way, what the answer is. Phrased this way, as far as O is concerned, psi is just a source. So if I integrate out n equals 4, these two pieces are just going to give me the generating function of correlators of O. Yeah. The only difference is, since I'm keeping track of causality properties and I want to keep track of the real-time physics, this is not the standard Euclidean generating function, I want the real-time generating. So the physics of time is basically S right minus S left, the bare ones, just the free field part, plus the, let me just call it S gen of psi right side. This is the generating function of real-time correlators.
So I'm thinking of the whole system as living on a Schwinger-Kelvin counter.
I think the whole thing system is living on Schwinger-Kelvin.
And the n equals 4 system, is it in the vacuum state?
No, it was in a thermal state. So like here, the environment were always thermal. So this is that finite element.
But the scalar field is
The scalar was in the vacuum. Yeah. So I didn't. So the stochasticity is going to be induced on the scalar from the fact that the n equals 4. You could take some other state for it. Scalar, insofar as the calculation is going to be concerned, I'm only going to do this part because the scalar part is the piece of the scalar that doesn't care about the environment goes wrong. Okay, so what do we expect? And this is something that you already mentioned. If you look at the answers for these generating functions, if you look at, for example, the low point functions, 2-point functions of retarded response. You'll see that there are two kinds of operators which I'm going to have to distinguish. The first class of operators, which is why we started thinking about this all in the context of holography, are those whose correlators decay on thermal timescale. So correlators decay exponentially on thermal timescale, and the only scale the problem, because this is conformal, is this thermal timescale. So these things. The correlator has an analytic structure which only has poles in the complex frequency plane. So I'm Fourier transforming to frequency domain. The poles are gapped from the real axis by an amount set by F. So I'm going to call this class of operators Markovian, and your generic single trace operator of, let's say, a scalar single trace of some dimension delta is of this. This is another class of operators that we're going to be interested in, which is why we have to make this distinction, which is operators like the stress tensor or any other conserved current, which in addition to these gap polynomial modes also have additional hydrodynamic polynomial, which are ungapped In particular, I'll define the gap, these guys as non-Markovian. And in this case, the frequency is a function. I'll work with translation in embedded systems. We can put this on we can put an IR cutoff in space if you want, but then everybody gets gap. I'll define this to be non-Markovian if the frequency goes to 0 in the limit momentum goes to 0. So an example is the diffusive mode, which comes from the ij 0i, the momentum flux of the stress tensor, or the sound mode, which comes from the energy density correlator, AES5.
Non-Markovian just means long.
Non-Markovian just means long. What it's not.
Yeah.
Highlight, in fact, and I'll come back to later. I only talked about the momentum flux and energy density, and they already have very different dispersion relations. I haven't talked about the shear strain operator, the TIJ component. That guy is Markov. So given conserved current has many pieces which itself behave very different. So we're going to have to confront that as we go along. Okay. So what we have to do is figure out, in this case, it's sort of clear what to do. You just integrate out the n equals 4, and this operator doesn't do anything, everything is capped on thermal scales. So this effect generating function is local, and therefore the effective action for psi is local. To be true in the case where you have a non-Markovian mode, if you integrate out n equals 4, these correlators are not local because they're poles which are sitting arbitrarily close to the real axis, and therefore this generating function is not local. We cure that, but we'll have to figure out how to cure that while respecting the fact that different mode theory.
In this case, it's local.
In this case, the generating function is local.
No, but n equals 4 has all both these operators, right?
So that the problem depends on what I couple with, right? So it's something like a thermometer, which I'm inserting in my n equals 4 plasma. So depending on what psi couples to, the psi generating function will either be local or not local. So if I take a psi and couple it to a single trace, let's say trace f squared, right? That's a dimension 4 operator, nothing happens. Then I just get completely local dimensions. But if you take it and couple it to a stress tensor, or one of the R currents, then I'll end up with this scenario for some reason. The answer is clear, which is very obviously clear from Wilsonian logic, which always says never integrate out in such modes, and you just don't compute the generating function, you compute it later.
Yeah, I was a bit confused because even with size coupling to some Markovian mode, when you are constructing the effective action, you are integrating out everything.
Yes, I am, but the thing that ends up here is just the generating function of O correlates.
Is there a way, sorry, you might of course say things like this, but is there a way wherein the hydrodynamic, so you integrate everything else out, right? That's in the spirit of it.
Yeah, that's what I'm going to do. So I'll make that precise after I tell you the other things. Yeah.
Mukund, can I ask a question? Yeah, so when you have the non-localities in the kernel in time, so I'm familiar with some situations in which like the RR guys and the LL guys, they have a specific kind of non-locality in which things depend only on the past times. Not it's still non-local. It's like theta of t minus t prime. But RL has, the full non-locality depending on the past as well as the future times. Is there something like that happens here?
I mean, I'm going to work in a slightly different basis, but the basis is more adapted to causality, and retarded response, of course, only is causally ordered. So it has non-locality up to standard retardation. Was that the question? Or did I get that wrong?
Yeah, so you're saying that your non-locality never involves future times.
Only involves future time, it doesn't involve past times. You respond, response
I mean,
is
not,
of
not
the
both.
good.
Not,
Not
both.
both.
Yeah.
Good. Okay, so let me first talk a bit about how to compute SGen. Yes. And then I'll come back to how to deal with the presence of this split multitude of modes in a single group. So, of course, people have thought about this problem of how to compute this generating function, and the first description was given, yes, 20 years ago by Soren Stalinets, which Soren Herzog tried justifying, and then Skenderis and Van Rey thought about it, and Van Rey gave a proposal, which is the one I'm going to talk about, which was amplified and clarified by Crossley, Glorioso, and me. The question is really this: what is the gravity dual of the Schwinger-Keldysh contour, which keeps track of causality properties? And since we are going to talk about thermal physics, I'm going to talk only about the Schwinger-Keldysh contours, where the state that's prepared in the far past is the thermal state. Okay, the Schwinger-Keldysh contour, of course, makes sense for arbitrary density operators, but that's not what I'm going to talk about. So these are the right fields, these are left fields, and for future reference, I'll switch between various conventions. So there's the standard basis that's adapted, that's well defined for any Schwinger-Keldysh system, which is the right advanced average difference basis. But there's one which is actually well adapted for what we want for thermal physics, which is a slight modification of something called the advanced retarded basis. And let me just give you the definition of the advanced retarded linear combinations so that we have that for the future. And this guy involves some combination of both Einstein factors and the right-left sources. So J suggests sources or operators that matter. So F is retarded and P is advanced. What did NB? So NB is the Bose-Einstein factor. Sorry. Oh, and I'm only talking about bosons, so this is frequency domain business. People have worked on the story for fermions, those have worked with these students, but I won't talk about fermions. Okay, so that's a question we want to ask, and the proposal, which I'm going to try to first describe in words with a picture, and then justify is for it. The state in the far past is the Euclidean is the thermal state, which I can prepare by taking the field theory on the thermal circle. So this is the circle of period beta. Its bulk dual with the theory of high temperature, which is what I'm going to assume, is the Euclidean black hole, the cigar. Well, so logically it is, but we draw the cigar. And what I'm going to do is I'm going to take a cigar and cut a slit on it with this of whose width is in temporal width is epsilon. And I want to evolve forward and backward on the two ends of this. So bear with me because this picture is sort of slightly misleading. This is Euclidean, and now I'm going to on top of that draw the Lorentzian picture. So I've just taken a picture on the boundary and turned it 90 degrees and drawn the circle. And the question is, what do I fill this with? So there's a natural filling, which is you just fill it with the Lorentzian black hole, but only up to the bifurcation surface, and therefore only to the exterior of the horizon, sun equals 0. Except that you could either do it this way. Actually, the way Van Rees wanted to do it is he wanted to take the disk and he wanted to erect two sheets which were glued on the horizon null surfaces. We're going to do that thing slightly more smoothly. We're going to deform the give a contour description that doesn't involve the gluing on the future horizons, but deforms that contour flow. Okay. An alternate way of thinking about this.
Sorry, yeah, that line which take goes from one end is Lorentzian, the other is Euclidean. The bottom is Euclidean. So
One is Euclidean.
but is a complex geometry.
Yes. Yeah, it's a complex geometry. In fact, it's a smooth complex geometry. There is no horizon, it just smoothly goes over. You just fold over tops. It's two-sheeted complex geometry. You fold over the top. And the two sheets you can think of as follows. The right sheet is one copy of one domain of outer communication of this black hole, where time runs up and therefore you get to fall in. But you never go anywhere near the singularity because as you fall in, you emerge on a second copy of the black hole. And at the level of what we want to compute, something is very clear. You get to insert sources in the Schwinger-Keldysh contour or the boundary on either leg of the Schwinger-Keldysh contour. Those are like psi r and psi l or jr and jl. All you need to tell me now is how to solve any bulk problem, compute Witten diagrams on this bulk, with subject to boundary conditions specified by these sources. If it's a double Dirichlet problem, the boundary conditions on two boundaries, the left and right Schwinger-Keldysh boundary. There is no boundary in the interior of the space.
Why can't I fall into the black hole? What? I mean, I see that the geometry, that's the proposal, but
This is the minimal thing you can, well, this is not quite the minimal thing you can do. But you don't need to go, first of all, causality demands that I can't get stuff out this way. So things can fall in from one side and they can sort of come back out as if they're sort of being rotated back on the contour. So the proof, if you like, so this is a proposal, it's not a derivation. The proof, if you like, is in a while I have to tell you that there are certain rules that correlators computed on this contour need side and side. Okay, I'll tell you what the rules are. So the rules are basically actually very simple. So one set of rules is basically if you put the same set of sources on both sides, you can collapse this back to the far past. Okay, so that gives you one set of rules which in usual language says correlators of just D, operators of 0.
Oh, which ones are 0?
It's D, because they involve the same set of sources on right and left. If you say J right equals J left, then operators are coupled to those guys. The other thing is, but there's one more thing, which is if I have an operator here, I can take it back down through the top, through the Euclidean part up. But it doesn't, as you conjugate an operator to the density matrix, it doesn't pick up a phase, it shifts in imaginary time. So in frequency domain, it picks up a factor we don't. Okay, so that gives you thermal periodicity condition. That's the Lorentzian analog of the fact the Euclidean correlators are analytic in thermal strip. And that guy puts another set of relations between various correlators. Okay, so they're easy to write down. For example, they tell you that the correlation function of two operators AB, the commutator AFT. Is 0 with a theta function, let's say, is cotangent hyperbolic beta omega over 2 Fourier transform. The correlation function Fourier domain of the anti. Change this to Fourier transforms. So in fact, this is the way statistical factors arise in correlation. They come because you can take operators through competence.
Also, if I had inserted sources only to some finite time.
Yeah.
And the rest of the time propagation is free.
Good.
I could
Indeed.
collapse it.
You could further collapse it.
And then is there a way to?
So yes, there should be a way. We have worked, that's why I corrected myself. I didn't say the minimum. It's not the minimal contour because we're running time on maximum future infinity. So it's a bit overkill. You're quite right that I should be able to draw a contour like this. So if, let's say my latest operator insertion was here.
Yeah.
I should be able to draw a contour that caps off here and then comes down like this. It should be possible. It's just some random space-like surface in the black hole. There's nothing fancy about it. But we have not managed to make it work. So we're going to just stick with this semi-minimal proposal and work with it.
And then the check would be that the calculations done in both the geometries agree.
Exactly.
It doesn't matter whether
Exactly. And to go back to the earlier question, you could do something more maximal, which is that you could draw fingers here, which could reach up to singularity. But you don't put bulks, you don't get to put bulk sources. Yes, because they know bulk source is a boundary source, that boundary for layers. They should cancel out.
Right, just to say, I mean, not that anyone's worked this out, but as Mukund and Diksha and I and other people have been discussing, the mathematical problem of what to do is very clearly defined. Okay? Because we know the rules for what to do to compute Euclidean coordinates. And then we know you have to analytically continue in boundary time. Okay. Now, presumably, what happens is that when you compute Euclidean correlators, you have to integrate over Euclidean bulk. Okay. Now, as you analytically continue with the operator insertions in boundary time, the propagators that you use in the Euclidean bulk would somewhere go singular. If you continue to do the bulk integration over the usual Euclidean bulk, because they would become time-like related.
Go from space like domain to time like domain.
So you'll be forced to change your bulk contour. And this will be and the rule will be that you have to change your bulk contour so that you always avoid singular. And this will presumably be one way. I suppose there are zillions of others.
Exactly. Because of what Abhijit said, there is there's a minimal thing that you just need to, and that's clear from what filter is. And once we do that, basically dictated by what last operator insertion is.
But actually, I just wanted to ask, I mean, since your complex geometry has no boundary other than the LR, wouldn't the natural thing be to say regular in the sense of solutions with the complex geometry background, regular in the interior subject to the boundary? I mean, okay, but it has to be proved.
And I think the interesting thing is what happens there. Yeah. These two contours, they sort of match up.
So Euclidean.
It's this part. It's going up. Yeah. And then there is curving and coming down. That, let's say it curves and comes down over a distance epsilon. It goes from Lorentzian to Euclidean. So it's all in a complex game. Yeah. It's clearest to think of it in terms of contour integrals. Yeah. And just deform the contour.
So let's do that. So the prescription, which I think is the cleanest one.
Can I? You mentioned about other states than thermal states. So, for instance, suppose you had some kind of a pure state, which was like a microstate of the black hole. In the n=4 superangles theory, it's probably some difficult game. But in ADS3, the Maldacena-Hartmann has the pure state construction in terms of the boundary states of Calabrese-Riccardi. And I was just wondering whether there would be a bulk representation of that kind of a thing.
Okay, so Gautam, I think in principle, yes. I know the cleanest theory for this state. the way, everybody's thought about the Calabrese quench type, global quench type constructions with boundary states has been to do the calculation Euclidean and then post facto weak rotate.
Yes.
But there should be a way to set that problem up like this without going to Euclidean signature.
So in like in their paper, they also have this geometries in which they draw a vertical line, let's say through your Penrose diagram, and say that you are just doing a Z2 quotient.
I mean, their Penrose diagram pictures are all fake because they're doing Euclidean calculus. Sorry. That's an interpretational statement coming from Euclidean calculation. I mean, there's no Lorentzian calculation that anybody has done in any of those contexts, including equity CFTs.
All right. Okay.
I just want to make one comment. I'm sorry for the interruption, but there's a similar issue as you move in terms of defining wave functions in discrete space.
Yes,
right. And there you can have either, at least in 2 dimensions, this is only in 2 dimensions, you can either have the continuation from Euclidean signature to Lorentzian. This is the famous sphere.
Yeah.
But you can also do AD minus ADS to De Sitter. This is the famous Mallasina contour. And I'm just saying, there you can show that as you change contours and so on, the final wave function stays in there. Okay, I'm just saying, in case it's of interest.
Yeah, I suspect it will be very similar. That you have to do many different, because the rules for contour manipulations are vast.
Yeah. I mean, exactly. It cannot one-dimensional contour integral. Then there is a lot more room to play.
And there, sorry, just to say, the way one establishes that you get the same thing, even including determinants, it's just for analytic problems. You continue the determinants.
Okay, so let's translate that picture into a contour prescription. And this is what CGL said. So the horizon of the black hole is here, and the boundary is here. And instead of doing the contour over the real radial axis, you run a contour that's, depending on your perspective, either called the Hankel contour or a T-hole, or just a branch cut contour that encircles the branch cut contour. So, notice what has happened. The contour ran up and down in complex time, but as you take this contour and fold it down onto the zero time slice, is basically translating that contour into a complex radial. This is the complex radial plane. And for later reference, I'll just define the following coordinate to the differential, let's say. When I'm going to take my black hole spacetime to be some non-extremal black hole with a non-degenerate horizon. And for simplicity, I'll just take it to be planar lineares. Okay. So this zeta is like a convex coordinate. I'll just rescale the convex coordinate by some factors to make some monatomic properties look nice. But it's, and I put the complex things where I can think of it as an excursion into the form up and down.
Yeah. So just for something you see that thing is basically what's happening at that tip. Right? Because time is going up to infinity. And then coming and meeting sort of like at the tip of the cigar. Now the tip of the cigar, time and radius are mixing. Time was an angular direction and radius of the. So see what that means is this.
And as Shira said, it's in the field theory, you don't see it because this is a boring place. Whereas this is the interesting place. But the bulk geometry mixes both of those up because cigar mixes a stand circle and the radial direction collapses it. So let's do something simple. Let me first set up the problem and I'll just give you the rules. In fact, I'll just convince you the rules are very nice. So what I'm going to do is basically just for a second talk about some wave equations in this geometry.
So this was Hong's main contribution.
This was main contribution because the picture
was okay.
the picture was older, but this contribution was.
But this lecture,
This lecture satisfy Einstein's equations, or we need some special properties of this.
No, I mean, the point is that the picture satisfies Einstein's equations simply because this satisfies Einstein's equations. Everywhere here you satisfy Einstein's equations.
I'm just worried about the wave conditions.
But I've just gone off in the complex. So this satisfy variational principle. You can go, for example, use the logic that we use with the paper with replica one was with Don G. Dong, Don and our student Colin Heller and Jensen Wang. We sort of gave a general argument for how to do replicas, and you can basically do this. So actually, in the appendix of the paper, we have some heuristics for why this might be the right.
I don't think you should look at a new solution. You're choosing a contour, and the complex holds.
Yes, that's a better way to say it. But it's really the solution. It's just the radial contour is not running along the real line, but it's running along the radial. Now, I mean, the thing is that since it's an equilibrium geometry, the complexification happens in one coordinate. That will not guarantee. In general, if you have some inhomogeneous space, then you might want to complex.
Zeta, right here, I mean, this is d zeta over dr, I'm just trying to understand, and then there's the standard infalling and return type of coordinates.
Yeah.
Complexified. Anything.
Tortoise coordinate. You just integrate zeta, the tortoise coordinate, you don't have this.
This is like the standard time, angular coordinate.
No, it's tortoise.
You're just saying b is some t plus r star.
I've already done that. But I'm not calling it R star because I beta factor.
So can you call this contour on this diagram?
On this diagram, I think of it as going this.
Sorry. So should I think of this as a deformation of the finger contour, which is this way?
Yes, it's sort of see because the moment you come in, as Shiraz said, as you come in, it's sort of aligned with ingoing slices. And the ingoing coordinates, size of constant r, the constant b are radially ingoing, but r is not. It sort of pulls down, and the boundary time agrees with b. But as you go in, the thing that becomes falls in is the radial direction. So let's see. I want to say a few technical things for a second, so bear with me. So let me introduce these two derivatives, which are, so this is not an orthonormal basis. So I'm going to define some derivative operators that are a bit more nicer to work with in this non-orthonormal basis. This is sort of a right basis for right tangent basis, so the d plus minus. So we can think of d plus as some kind of ingoing derivative and d minus some outgoing derivative for reasons that become clear. And if I just write the standard scalar wave equation, let's say for a minimally coupled scalar, in these coordinates, so because this could be dual, this file could be dual to my operator O could just be a minimally coupled scalar of dimension delta. And yes, was there a question?
This is a scalar wave equation.
It's just a scalar wave equation just in this adaptive phase. I'm just going to tell you how to set up the rules for doing in Witten diagram in the job. So the first ingredient. So you want to solve the double Dirichlet problem. So I want to solve it with sources put on both boundaries. So the first thing is you just go and compute the ingoing pulse to boundary propagator, which you can think of as a function of r, omega, and k. And this guy satisfies two boundary conditions. It's normalized to unity as r goes to 0, as R goes to infinity. Okay, maybe I have strip off some powers of R, but doesn't matter. And it's regular at the horizon. It's analytic at the horizon. Now, one advantage of working with these ingoing coordinates, and this is a statement that's true not just for ADS black holes, the statement that's true for any black hole with a non-degenerate horizon, is that this differential equation has a regular singular point at the horizon with Frobenius expansion with two independent solutions. One of them is this ingoing solution with exponent 0. Okay, that's the point of the ingoing coordinates. It sort of makes that analytically manifest. In short shell coordinates, it not be true because it's not T is B minus R star. And the output solution is not analytic. It has a cut from the fact that the horizon is a singular point. And the cut is precisely set by beta omega over 1. It's this statistical factor that shows up. So this is the factor I tried removing by 1 pi. So in this theta coordinate, monodrome is 2 pi. Okay. So we're going to use this piece of intuition. And something that's helpful is once you've solved this ingoing problem, the outgoing Green's function, because of this monodromy factor, can be easily understood as follows. Technically, it's because these operators satisfy nice conjugation properties, but I could just tell you that in outgoing bulk to boundary propagator is the ingoing propagator with time reverse because it's going backwards, but not for free because it has to take this monodromy into account, and that's this fact.
And Mukund, I didn't understand this. What does in and out mean? I know we just have two boundaries.
So ingoing, I start the problem on one sheet.
Yes.
And I find a solution which sort of seems to be going in.
Okay.
So from this point of view, it's from this tight boundary, let's say, is a solution which is infalling towards the horizon.
Okay.
Or towards wherever that
Yes.
is. So if I'm coming from here, it's a thing that's sort of just going in, directed that way, like a plane wave. That guy is analytic. And across the horizon, it picks up a monodrome. Okay. So this guy is analytic, but there's another solution which is not analytic. The two linearly independent solutions in the horizon are these two. Right. So I've only picked up one,
Right.
And that's this problem.
Yes.
That's the problem you naturally try to solve. You're trying to solve, not quite, but a variant of the problem you try to solve is solve polynomial modes.
Yes.
There you would say that the wave functions are normalizable at infinity and ingoing at the horizon.
Yes.
I just changed that normalizability to explicit non-normalizable because I want to stop propagates.
So is this the same as saying that you've fixed 2 points, one on the left contour, one on the right contour.
Yes.
You satisfy the boundary conditions at infinity,
Yeah.
and you satisfy the continuity along this contour.
Exactly.
Okay.
Exactly. You pick up the right monodromy for the modes. All I'm saying is that there's one class of modes that don't pick up monodromy, another class of modes that pick up monodromy, and I'm just calling them in and out respect.
Okay.
Just confused between regularity. You say the solution R minus R plus to this power is not regular in the sense of not being analytic.
It has a cut at the
Yeah. So would you allow as per your
no, this solution is the one that is which by regular I mean it actually behaves like R.
okay, that's what you meant.
With the analytics.
So that's what you mean. So you're not going to allow the other one.
That's here. That's the other solution. This behaves like R minus R plus. That's in the zeta coordinate. Buried in the zeta. Because this guy is analytic, he doesn't pick up monodromy. Monodromy just factor.
That is just that fact.
It's exactly the same. Exactly the same.
And you're,
I mean, I could have just written it as a either private.
Just I was not very important.
sorry, just to know, what is the full solution? Is it in plus out?
I'm not done yet.
Okay.
So the reason I wrote it this way is that you see something that's interesting about this factor. This looks like a Boltzmann weight. But it's not a Boltzmann weight that is purely boundary. It's a Boltzmann weight that's modulated by where you are in the radial direction. So this to me is a very nice signal of saying that black holes behave like common objects. The radial Boltzmanns.
I'm sorry, Mukund, I couldn't read the circled thing. It's e to the power minus
Beta omega zeta. Beta omega zeta.
Beta omega zeta. Okay, all right. Thanks.
Okay, so now let's understand what the full solution is. So solution for pi is indeed some linear combination of G in plus G out. So these are two linear independent solutions. And now I just match the sources. So I get to set sources on the right and left boundaries. So maybe I keep this picture again.
Irregular. I mean, it's not analytic.
The solution is not analytic because of the second guy. The Hawking modes are not analytic because they're the outgoing modes.
It will be analytic along this contour.
Yeah, because they're going to avoid the cut. They're not going to integrate along the cut. We're going to go around the cut. So therefore, Ashira says that doesn't matter. So if I put those together, I can write the solution as follows. Let me write it this way: G in A plus G. Let me say this some what we call Hawking propagator doesn't matter. Some JT where GH is some combination of ingoing and outgoing propagators with Bose-Einstein. So that's a general solution for the scalar field with satisfying this double Dirichlet boundary. There's no sources anywhere else except for the boundary. I've just written it in this average station. You can, because all the bases are linear transforms, you can translate the PF basis into Colorado. How long do I go?
There's no time constraint.
When people start getting hungry and start leaving. Okay. Let me tell you one more thing. But what I wanted to bear in mind is that you don't have to solve complicated problems. This problem is easy to solve. This is the stack problem. That's a slight variant to call a normal problem. You know, almost everybody has solved this once in their life, and you can just adapt it, make this. And once you have the solution, other solution is easy to write down. Moreover, something else that's easy to write down is the following. The bulk propagator is also easy to write down. And I'll need that for what I want to do. So that one I'm going to write as a function of let me write it as a function of r prime to coordinates omega. And this goes, I want to emphasize one factor, so I'll write that factor. There's a beta omega zeta prime. 1 plus NB are used. And okay. If someone wants to know the formula desperately, I'll write it, but let me say it's something. Okay. So product of the in and out solution. These are two linearly independent solutions. Then you can just use the Wronskian rebuild the bulk. Right, and this theta function ordering is radial contour order. Something else happens, which is important. One second, Shiraz. Yeah. In the boundary, there was temporal ordering. The Schwingle-Keldysh contour is time order. So contour ordering is time ordering. But I don't have time contour, it's just the radial contour that become complex. Contour ordering got taken care of in the boundary by going to frequency cover. Just cut off frequencies appropriate. However, when it comes to the bulk to bulk propagator, something comes back in this radial contour. Yes, yes.
Yeah. So bulk to boundary propagator, just to understand the boundary conditions could be put on either of the two boundaries.
Yes.
So you've got one delta function either here or there, and 0 everywhere else on both boundaries.
That's right.
And then it has to be regular around this.
Yes.
So that clearly defines.
That clearly defines the problem. Double Dirichlet does. And the bulk to bulk is something of that kind. And I put quotes for in and out because they're not quite defined in terms of non-normalizable modes. I took some linear combinations to make them normal. Yeah, I get from there.
Sorry.
Okay, so that's the statement for what we need from this problem. But you see, everything I need can be solved by obtaining invariant bulk form. At this point, everything is straightforward. You just put sources at will on the boundary and propagate them to the bulk and glue them together with bulk to boundary or boundary to bulk sources. The bulk vertices again, this is not going off this place, but it's going around.
And if you wanted to solve a bulk to bulk propagator, once again you just set it to 0 on both boundaries.
Exactly. That's why I put quotes here, but I'm not putting sources on either boundary, so it's
yeah.
So it's some linear combination of in and out, it makes it 0 on both. Okay. So that's the rule, but at this point, you see, there's no funny region of integration. The integration runs along this contour. This contour is well posed, as Shiraz said, you're off the cut. Lack of analyticity doesn't bother you. And it goes nowhere in the singularity. Okay. So it's as well posed as any Venn diagram computation for regular correlators immediately. So we can go to town and compute this.
But I mean, what's the proof? Like, is there, can we check this?
Let me continue. So this guy, we should check that it works, and here are certain statements that you can check. I said that there's some statements about the KMS rules about how things go around a thermal circle and how difference operators correlators. That statement in this retarded advanced basis a correlator of a sequence of P is an arbitrary sequence of P operators, 0. And a correlator of an arbitrary sequence of F operators is 0. And these are the only constraints in this case.
P was again what? This one. So
Retarded. So these are all the rules that a single condition thermal field theory is satisfied. So if I check them, I'm done. That's at least consistency check that they're not doing something. Second, of course, I have to tell you that it computes right calculator. And this is where things start getting violently tricky, but can be done. So
the similarities of the Schwinger-Keldysh correlator are also dictated by like, right? Even if this just works because it just comes out like same.
exactly. It's the same light cone property because in some sense, I'll say a few things about this guy. Second, you see how the light cone study works very.
Very sorry, I keep interrupting you. Please excuse me, but these rules apply for bulk fields which are dual to all operators, right? Not
Yes.
necessarily those which are conserved. Such.
Okay. So let's say a few words. Let me just say a few.
Sorry, one more interruption. Just it must be obvious, but if you had insertions on only one contour.
Yeah, that's like a piece here. That's like all P's because P is like D, which is some statistical sign.
I see.
So in some sense, actually, I can tell you what this is. This is like. See, okay. Let me say one thing that. So the PF translation to JAD is like P is like difference, but F is not like difference, it's some combination of average and difference. So all P being 0 is like all differences being 0. And this is sort of a bit more annoying because it's NB plus R. So there's some nice things. So look guys, you said one side.
Oh,
You said one side.
one side, I was saying one side. But
No,
maybe this is more interesting.
Yeah, but one side is not 0. Right?
It's not zero. No, what I was getting at is that if I built usual retarded correlator,
Yes.
One should be able to solve it by just ingoing.
Correct.
I wanted to see that from here.
Come. So I'm excited that because I just want to show you the corresponding. So I'll tell you what the retarded correlator is, and I'll show you that it has the right analytic structure in frequency domain. That's all what matters.
Yeah, but even the solution should be somehow just ingoing.
Right. So, anything else? Okay. So with this, let me say a couple of things about proving these statements, and then I'll come back to what some corollaries of this. Which you can. If you didn't have bulk to bulk propagators, they are only contact diagrams, you can convince yourself that for most interactions, these contact diagrams, you're doing an integral around a cut, and all contact diagrams basically pick up a discontinuity across it. So cut integrals will basically pick up a discontinuity factor, and the integrand is just the discontinuity along the. That discontinuity, because of the zeta factor, this e to the minus beta omega zeta factor basically morphs into something like 1 minus e to minus beta omega. So statistical factors come from these radial integrals. Because they're partly there in the propagators, but some more of them come out from. And they make sure that all F's, for example, have no paths, have no discontinuity. So you evaluate product of all the ingoing propagators, and you find that there's, so in fact, I should have just said maybe that if you just look at these factors, the thing that multiplies the ingoing guy is the F, the thing that multiplies the outgoing guy. And so immediately it follows that there's no discontinuity to all these correlators. I'll say something about the exchange diagrams. Likewise, for the P's, it works the same way, except that you have to use overall momentum conservation. Once you use overall momentum conservation, then again there's no discontinuity, and then the correlator is collapsed. So you don't have to calculate to check that these are true. These are just manifestly true at the level of the concrete. For the bulk-to-bulk exchanges, you have to do a bit more work, and we use the analytic properties of in and out to show that it works at 4 and 5 points. Because you see now, these bulk-to-bulk propagators have theta functions. So it's not just a discontinuity across the cut, but it's also the discontinuity from the jumps across theta functions. So I think the argument which we are giving in a paper that's come out tomorrow, we show explicitly how to do 4 and 5 point functions with 1 and 2 exchanges. But I think that process iterates, and one can just give an iterative proof to say that all orders P's and F's are done. But I have only checked 4 and 5. Logan, Dispute, and Godwin have checked up to 6.
One think of this to the minus beta omega zeta factor as like a coming from modular flow and about. It's like a sort of KMS factor coming from about and the
Yeah, I mean, this is the sort of the simplest modular flow. In fact, only modular flow anybody ever solves, which is the flow along the curves for real local
from the bulk point.
Well, from the bulk and boundary point.
From the boundary point of view, it's clear, but I was imagining that this the minus the fact that there is a log R there.
Perhaps. I mean, I'm not quite sure how to write it in the bulk. I will tell it, but perhaps.
So, just one question. So, one way to diagnose bulk locality is to look at the bulk point singularity.
Yes.
Of various correlators.
Yes.
And this prediction, in this proposal, would have a prediction about where this should exist for this mixed correlators. And
Yes.
Then one can see from CFT whether one expects such a thing.
I totally agree. So, in fact, the story here is not simpler than the bulk point singularity. So remember, the bulk point singularity was for n plus 2 point functions in n dimensions. There are 4 point functions in CFT2, and that basically was governed by the fact that 4 null geodesics could meet at a point in the bulk. I'm already in the thermal state. 2 point functions are sufficient. Okay, so in fact, way back when Hong Liu, Veronica, and I gave a statement that if you compute these correlators, there's a GR statement that you govern wall that in excited states, which are not in actually there's a time delay statement that govern wall proof that in excited states various. If you send signals, they should arrive at the boundary slower through the bulk than going around the boundary. That's a statement of causality. So any additional singularities which are not dictated by boundary causality have to be inside the boundary light bulb. So it's the kind of statement that you have to make in the beginning that you see this path broadening, it has to broaden in the right plane. It can't go off somewhere else. Right? Nobody's checked it, but I think it should be nice. It should be a nice check of the discourse. Okay, but just to wrap up what I was going to say, for exchange diagrams, it's a multiple discontinuity coming from this theta function convolved with the discontinuity coming across.
It was just to sign up being into this field. Is this enough to prove that the contour is correct?
Yeah, those are the only relations in field theory that we need to satisfy. I'll say some more things about the analytic structure.
You need to satisfy, but is there just at the level of correlation functions something you could have computed in conventional ways which you can test against this? What I mean by that is you can compute the retarded range functions in conventional ways without needing
In some couple any plus four.
no in the bulk we know how to compute from gravity
Ingoing boundary.
ingoing boundary conditions and
That's exactly what was on. But now.
okay, but what I was getting at, and then because you would say, is that suppose I just did the same kind of calculations for your correlators here in Pascal. Does it match up with this? Then maybe I haven't made it precise enough, but
I don't see what bulk calculation you want me to do.
usually we need future horizons and ingoing, and then you compute all correlators, right? All retarded range functions and all. I think
But what do you compare with that? I'm doing 88 CFTs. I'm only have boundary corollary.
No, I think Sandeep's asking, you've given a more general set of rules. Now specialize these rules to the computation of the returns correlate, and you get only input.
Yeah, that's
I would say so.
I'm not trying to. And that's putting it along one contour, right? You know, or no, I
Commutate.
some.
Yeah, it is a formula. Yeah. This. Okay, so can show the following to be true. Okay, let me get one more question. There's one context that you can actually do it. So the challenge here is to do analytic calculations and wave equations in black hole background like the one I know I wrote down are not analytically solvable in check. There's one place where they are, which is PTZ. And there you can just go to town, you can compute these things and check that what you get agrees with conformal to reconformity. Okay, so that in principle is answers the question where it's asked. But what you can show is that the retarded propagator, so if you look at G, it behaves at infinity as 1 plus, let's say, let me talk about a massless scalar field, so this is simpler. Delta equals T. It behaves like this. And this guy is the boundary retarded Green's function on the nose. Okay. So the singularities of Gn are the singularity of the boundary retarded Green's function. They are all the quasi-normal modes in the lower half. And moreover, then if you go look at the outgoing propagator, it has its monodromy, but apart from the monodromy, it's basically the time reversal of this guy, so it has polynomial modes in upper half. So corollary demand that incoming guys are analytic in the upper half plane, and outgoing guys are analytic in the lower half plane. Two by virtue of boundary conditions. So that's not an input.
Yeah, okay. Sorry, you said this, but I'm just doing it. So if I were doing it purely in terms of Lorentzian pictures, you're drawn two black hole horizons. One was ingoing, the other was outgoing. And in that picture, how are you pasting the two? Basically, whatever goes in through the first picture comes out in the other.
Yes, with appropriate monodromy.
Sounds that's nice. And then it follows obviously that these will be regarded. Okay. Just like construction.
Actually, even that it wasn't totally obvious to me.
Yes.
It has to be that when you do the right thing, you get exactly GA.
Yeah.
Which is what he said works, but I couldn't see that. Yeah.
So it's too fast to say that you're pasting what goes in, what comes out.
No, that's okay. But you're putting boundary conditions in a particular way to get the retarded correlate. And that should have set the G out part to 0.
Does it?
Does it?
Yeah. Okay.
Okay, so let me then say something more. Already at this abstract level, then I'll tell you something about actual correlators. We have computed over the years. You can now just examine higher point functions. The 2-point functions are done because the retarded guy is this, and this is the coefficient. So in fact, I can just write down the 2-point generating function. It's k in. So the boundary is gen. At the 2-point function level is some integral over momentum space. It's k in omega k, which is the retarded Green's function, jd plus.
Just a tangential question.
Yeah.
Does there exist a prescription, a bulk prescription for computing out of time order correlators even in the vacuum state? So this
should generalize. Nobody's managed to make it work. And then nobody actually computed out of time.
when you have these folds on the boundary, just even in the vacuum state, how this boundary, how this geometry is into a folded fashion.
And it's precisely this analytic continuation method that will then tell you how you think how. Okay.
Yes. So this is the structure of the generating functions. If I write it in any base in the PR basis, it is. And that's why the PR basis is nice. This is just a PF property. There is no PPO. Okay. So that's a statement at the level of 2-point functions. I can now make statements about arbitrary endpoints. So let me just make a statement. Assuming something about bulk radial integrals, which I have to assume something about the dimensions, make radial integrals converge without being counter-doubling normalization. I claim that a correlator of a string of p's and a string of f's has, let me call them anti-quasi-normal modes. These are quasi-normal modes in the upper half plane. And this guy has quasi-normal modes in each of the frequency labels. Okay. In addition, on every factorization channel, it's an FF factorization channel, there are only quasi-normal modes. If it's a PP factorization channel, there are only anti-quasi-normal modes. With a PF factorization channel, there are both. And these are the only things that are possible in hologram. This statement is used to me because I didn't know whether cuts couldn't appear from radial integrals for higher.
What is factorization channel? It's a tree-level type, right?
It's a discrete level.
Why were you expecting cuts?
Well, I didn't know what to expect because nobody checked it. But yes, the statement is that, in fact, it's actually something very nice you can do. You could just take G in and factorize the K in. Okay, and then you can just write down a radial integral of some nice analytic function. It produces one extra, which I'll tell you. In addition to so radial integral convergence in this logic also tells you something stronger. It tells you that the correlators are actually obey appropriate radial integrals. There's a convergence condition of the radial integrals coming from dimensions. So if the dimensions are too large, then the fall-offs are at infinity because I've turned on normalizable modes is slow. So I have divergences from there which I have to counter on the unit. Those are benign, but I also get divergences from these beta omega beta factors. These are the factors I got from the outgoing nodes. So these guys give me some additional divergences, which tell me that the correlator better be analytically appropriate. It says that all the p's, anything that has p's or factorizations of p's into something, only goes or is only required to be it can only have non-analyticity in the upper half. P's are analytic in the lower half. And they likewise are analytic in the upper half and can pose in the lower half. So what this allows for is, in addition to these guys, it allows for what I call Matsubara. In exchange.
Very sorry, but there was something I'm not understanding. I'm thinking of as a particular linear combination of insertions in the boundary.
Yes.
What does it mean for a P to be exchanged? How do you associate a bulk mode with it?
So suppose you're doing boundary diagrams with this.
Yes.
There's only a PF property. There can only be a PPF or an FPP vertex, FP vertex. Because all three, for 2 and 3 is clear about what it is. So I'm saying that when the P's go into F,
whatever it goes into, you're going to call it F.
Yeah, it has to be F, so the pole that diagrams.
Okay.
So, but I'm saying that in addition, these poles are allowed. What are these poles? These are poles exactly at where e to the beta omega is 1. And they might be in the, if it's an F exchange, these poles might be in the lower half plane. P exchange might be in the upper half plane, or if it comes from the factorization of P and F, can be again. So this is the full analytic structure of a general.
So can you say a little what these poles were?
So I'm saying that the way the calculation works is that you can factor out these boundaries above properties. So this part where I just said there are only anti-polynomial modes in this guy, only polynomial modes in this guy, or in the exchanges, that part is manifest without doing the radial integral. The radial integral can produce additional poles, but it doesn't produce poles that care about the dimensional operator. It produces poles that are just thermal factors. They're sort of universal poles. And they exist at very special frequencies, which are the analytic and included frequencies. That's why I'm calling them mass. And all I said was they are where they need to be by causality. They can be where they need to be, but they're always dictated by causality.
Suppose I looked at the problem where I said all boundary conditions to 0.
Yeah.
And I demand, meaning I demanded normalizability on both boundaries.
Yes.
And I demanded regularity on your contour.
Yes.
Then do I get solution both on these lower half poles and the upper half poles?
Yes, I think so. Yeah, because that's the problem you solve for the bulk-to-bulk propagator.
Yes.
And the bulk-to-bulk propagator, remember the product of an in and an out.
Yes.
Right? Clearly has both.
Yeah. So this problem has propagating modes here and there.
Exactly.
Therefore, those propagating modes can run in.
Exactly. Exactly. So the bulk exchanges, they do exactly what you're saying.
Right. Of course, the complex propagating modes and so on.
But so, in some sense, in this problem, the quasi-normal mode are the particles. They are the physical states that we data is basically residues on those polynomial. There is particles with half-lives. Okay, so that's a general structure. So we know all this from both general arguments and from a toy model that we worked out. But to tell you about the toy model, I need to go back and tell you a little bit about this distinction between Markovian and non-Markovian. And that will be quick because I'm just going to tell you a couple of facts distilling what we've done in a couple of sentences.
Sorry, one very quick qualitative question.
Yeah.
If I is there some reason? See, you've got these quasi-normal kind of modes and then these anti-quasi-normal kind of modes. So modes that decay in time, modes that grow in time.
Yeah.
So are there correlators that grow in time because of these modes, the exchange of these modes?
No.
Okay.
Yeah. This is related to some other question, but not.
There's some property of this that stops those from.
Well, if you look at the advanced correlator,
Yeah, they go. Right. So if you look at the right kinds of correlators, they will never grow.
Yes. If you look at appropriate retarded responses, they will not work.
And if I just look at time ordered correlators on one boundary,
Yes.
I take 2 down here, 2 up there.
Yes.
Will it grow in time?
Because it will have an advanced.
I see. So these things somehow are, and that's okay.
That's okay. It's like fun and IX stuff, right? One of them depends whether you go up and will down and up, or down and down, or up and up.
I see. It's not a big cluster decomposition, but that's okay.
I think this is the closest you get in this cluster. Okay, so I don't have to copy the generating function for general operators, but I also told you at the beginning that for special operators, I have this problem with the generating function.
Actually, I know, sorry. The only things that will obey this cluster decomposition are the data.
Yes,
Everything else
will have some mixture. Okay. And in some sense, that we should expect, because those are things be computed in field gravity.
Exactly. But
Yeah, because those are things that capture the transport data.
they clearly obey it.
Exactly.
But I was, yeah.
So now, let me say how to sort of break up this problem for something like a stress test. And the statement, which took us a while to establish, but It existed in the literature, but we wanted to have both the derivation done right and something that wasn't done in the literature, which is to compute actions, because everybody was the level of equation motion, is I told you that Tij, T0i, and T00 have different properties. They have very different dispersion relations. Famous fact that's known for many decades is that this behaves like a minimally coupled scale. It's a tensor polarization of the graviton that behaves like a minimally coupled scale. This guy is momentum flux. It actually behaves roughly like a gauge, like a current. It has linear DPOs are like linear gauge transformations, a million gauge transformations. But it doesn't behave like a Maxwell field in ADS. It behaves like a Maxwell field in ADS with its the Maxwell coupling having radial modulation. But let me do one more decomposition. Let me take that Maxwell field and break it up into its vector and scalar parts. And this is like the vector part of the scalar part of the Maxwell field. This guy also behaves like a scalar, but it has a so this has a canonical kinetic term. Okay, this has grad phi squared kinetic. Let me put a root G here. This guy has a root G grad phi squared, but it has some function of R sitting in front. You can think of some kind of auxiliary electron. And that's the only modification which is of relevance. There is a potential piece, but I'm not going to write out the potential because it's not very deep. This guy is awful. And it also has this kind of so let's call this vector and let's call this scalar. And I just have to tell you what these potentials, what is electron. And I'm going to draw them for you first and then tell you what they look like. So in the case of if I look at root G times this electron, which is sort of it basically tells you what the effective redshift sequence field is. For this phi field, it grows towards infinity. No, the unconvex, the first one. Slash VH. So that's basically saying that this guy behaves, it's steeper than the ADS potential, it just wants to fall in. They don't want to, it's not allowed to get out of the bound. The wave function is supported mostly. For var phi and psi, the potential does something like this. For var phi, this is just true. For psi, I'll tell you in a second what the further modification. This guy goes like 1 over r to some power. In fact, this whole thing goes like 1 over r to some power. Power depends on dimension. For ADS 4, it goes like 1 over r. It basically says that there's no penalty for the field to live here. So these fields hover near the boundary, which is why they're long. And trying to draw this correctly, there's no divergence at the horizon. There is a divergence, but it's at the same time. For psi, it looks like this, but there's a further complication. So chi v is just power law. But chi s is, I know off my head, so I can write it. It's the dilaton is modulated further by momentum factors. K equals 0 is very different from K not equals 0. Because this problem has solved. Problem has boundary gravity. These two problems don't happen. In fact, T equals 0 is a part of this problem that looks like this problem. So 0 modes, they don't produce sound because there's no sound without motion, and that guy is false. Only return a little bit of momentum. So these facts are known, and Shibashi were the first to work out from level equations of motion. The combinations I'm describing, these scalar fields are what they call master fields. They're basically just gauge invariant combination, diffeomorphism invariant combination of equations. And
there's some horrible potential for the scalar dynamics. It's a horrible thing.
Yes, scalarism. So we work this out for the, I'm just telling you the story for neutral black hole. We also work this out for charged black holes. Then the problem is a lot more interesting because there's gauge field and the graviton, and they both have both of these kind of modes. But at the linearized level, you can just decouple. You have to decouple them rightly, otherwise you sort of see all sorts of things. But a corollary to this, which sort of says that each polarization of the stress sensor we have, obvious for neutral fluid, but not so far. Yeah.
So some linear combination.
Some linear combination of T00 and J0 energy current, but then some other linear combination of charge current. The charge current diffuses, whereas the energy current propagates and then attenuates. So these are all being worked out. And I'll say it was important for us for collective. So the equation of motion alone, but we also wanted the actions because we wanted to compare functional actions. Moreover, at the very beginning, I told you we don't want to integrate out these type of modes. Okay. Furthermore, I'm also telling you that these type of modes are floppy near the boundary. So they are decaying very, very, very slowly. In fact, they're not decaying, they're growing. So trying to solve them with Dirichlet boundary conditions where I freeze the non-normalizable part is a dangerous game. Now, gravity, of course, is smarter than us, and it comes when you do the change of variables in master fields. It changes the Dirichlet boundary conditions for gravitons to Neumann boundary conditions for master fields. So it's not obvious; it's absolute mess. But when you actually go and examine the asymptotic behavior of the boundary terms, things fall apart. You actually get just the Neumann boundary. Once that happens, and this problem is straightforward, once we got hang of it, we work it out. In this problem, if you do the change of variables in master fields, the Knight action is fifth order in derivatives, but the action has a lot of hidden symmetries in these variables. You just collapse them into boundary terms. Boundary terms are higher order, but nevertheless, asymptotically just give a Neumann boundary. The Neumann boundary term, remember, is just linear. It's just the field times conjugate momentum.
Knight action is fifth order of the equation.
Our second order, which says that everything in the action coding is boundary. This is something that we have to check, where you just write down a fifth order action, compute its variation, and you find on the nose. You do the right change of variables, it's second order. Very so if you wanted to compute correlation functions of operators dual to these fields of these two, you should compute them with Neumann boundary conditions. So as the generating function is computed with Neumann boundary conditions. That's a tight boundary condition input to compute stress tensor correlator with Dirichlet boundary conditions for that. Okay. But we don't want to integrate out these fields. We want to keep them. What do? You integrate them back in, which is basically the Wilsonian language. Just don't compute the one PI generating function. Just add back a Legendre transform piece to put the field back. But the Legendre transform piece is precisely this term, the opposite sign. Therefore,
I'm sorry, somebody is blocking the camera.
therefore,
Thank you.
if you compute the correlation, compute the answer parameterized by field values and stress tensor, the operator expectation values of these guys. Let's call this E for energy and call this P for momentum. Those are basically the waves are just computed. The generating function parameter of the waves is computed by solving this problem with Dirichlet boundary. Standard correlation function generating function is computed by Neumann boundary. But this guy, which we call the Wilsonian influence wave, which is the right thing to compute, which has locality, is computed by one with the Dirichlet boundary. So I want to try to spell this out. And
you're doing you're only keeping track of the very low energy quasi-normal modes or also the heavy ones?
good. So excellent. So when we did this initially, we were trying to solve the wave equations in black holes and dimensional current ions, which we couldn't solve on any of these problems. That even this one, the easiest one. So we always solve them in gradient expansion. So at that point, we were only keeping track of the lowest quasi-normal. And so when we did the Legendre transform, we only kept track of it because every other quasi-normal mode was outside our solutions. Okay. For some problems, some questions is not good enough, which I'll tell you offline. But we wanted to ask what happens more general. So the higher dimensional problems are complicated because the wave equation even for these guys is complicated, but these things also have rigid potentials. So I don't know how to solve any of these problems analytically. But what you can do is you can take inspiration from this guy and you can cook up a toy modeling PDs, but you just put some kind of dilettante factor like this and study that problem. So there we just have the analytic answer for the correlators. And then when we do the Legendre transform, we just do it once. Everybody gets Legendre transform, which is a bit of an overkill because there's no way to isolate when you have full analytic expression one mode from an infinitum of discretum of one now. But if you take that answer and just gradient expand it, then you only keep the low line guys. Right. So in that sense, you can try to choose to do the Legendre transform and focus on just the low line. Yes. But it's an interesting question whether if you think of this as a tower of states, can you just isolate the lowest piece from a full analytic formula? So this toy model is really what gave us insight into various of these structures that I described to you before. But the toy model was obtained by doing this sort of calculation of how to repackage this. Someday we should actually compute vertices here and try to do the thing in the real model. Happen, but it hasn't happened yet. Okay, I think that's mostly all I wanted to say. Let me see if I want to say something. Oh, in the higher dimensional examples, there's another consistency check because some of the retarded correlators at the 2-point level have been computed by people over last 2 decades. And we know hydrodynamic data, even on a linearized level. So that guy, those guys we can check, and wherever data is available, of course, we reproduce that. Moreover, something that is interesting is that G-in, which would not surprise experts, is parameterized by the same data that the fluid gravity solution was parameterized. The fluid gravity solution was parameterized by some number of functions at first and second order. It's the very same functions that show up in G. So the wave functions are basically just those functions repackaged different.
Linearized fluid mechanics is just retarded code.
We not only have the retarded guys, we also have the sort of fluctuation associated with them. So in particular, we have the metric of fluctuating hydrodynamics at the linearized level at fluid gravity, which is something that we didn't get when we did the nonlinear. Okay. I think with that, I'll just say that this, I think, is a very general phenomenon that all the so we call these the non-Markovian modes, and these are Markovian modes, but they really capture physics of what's happening. And for massless fields, you can just parameterize them by one parameter, which tells you the rate of decay. I won't write out formulas. You can find formulas for various functions, 2-point functions in our various papers, and for the BDC case, read about them. With that, let me stop and take any further questions.
What's the final picture, if I can ask you? If you had something which was coupling to what you call a Markovian, so physically you expect, okay, after some time, it may start in its ground state, it's in contact with this sample reservoir, it will come, feel have fluctuations. In contrast, if there's a source which couples to the hydrodynamic modes, what is it?
Well, it doesn't, it normalizes, but it takes arbitrarily long time to normalize. The modes are long. So it's like the problem is very much like a superfluid, right? There's a superfluid mode. You don't integrate out, just keep it there.
So you have something which couples to the shear mode or something.
Yeah.
It takes a
a long time.
How long does it take? Depends on the frequency or something.
Well, so the effective field is only valid when the frequency is smaller than thermal scale. With dynamical regime, that regime.
Well, I mean, is there like the Markovian guys thermalize at time scales of order T temperature? These ones are, is there an interesting question?
Yeah, there is an interesting question, but here the frequencies are parametrically smaller than that.
It's just the omega of the sound mode and the shear.
Just the omega of the sound mode. Okay. Okay, yeah, that's the most reasonable answer. Yeah, because they go down all the way. So what's the other scale?
But just continuing that, there were these really interesting papers over the last decade by Rangamani and collaborators giving effective actions for hydrodynamics.
Logan,
one would perhaps have hoped that computing a Wilsonian effective action for these light modes would make contact with those actions.
Yeah. So what we know is the following. So we have various predictions from those actions. And for those of you who don't know what those actions have two pieces. There's a bosonic piece and some PRST piece, which involves some topological supersymmetry that we use. The topological symmetry is invisible in the research.
Yeah.
It's absolutely invisible, and I don't know where it's going from. But the bosonic part, which is the really operative piece of the hydrodynamic stuff, which tells you what the physical statements are, what the retarded response is. That piece you can just check agrees with our linearization of our predictions.
But those actions were non-linear.
Those were non-linear.
Is there some way of understanding that, you do this whole thing in some non-linear level?
Yeah, so one could ask the question backwards, which is, we have the linearized solutions to answer the equation from that contour. We also know on one half of the contour, non-linear solutions that some other people work. So given those two facts, can you put them together?
Yeah.
And as I told you, the reason I think the answer is definitely yes, because the linearized solutions are parameter of the same data. I know how to non-linearize that solution for one part of it. I just need to know how to non-linearize the other part. Right. So I mean, let me give an analogy. Some of you took a known solution, the Kerr black hole, checked the solution of linearized fluid dynamics on a rigidly rotating sphere, and wrote down the bulk solution along fluid gravity, and realized how you could correct it to get the nonlinear solution. So there's an explicit formula in one of your papers for what the Kerr black hole looks like in fluid gravity variables.
Yes.
Presumably something like that is true here. You just have to identify the velocity field and the temperature field, correct? I mean, that formula was easy because the only thing that was turned on was vorticity.
Yeah.
So what you got was some determinant of the vorticity.
Yes.
Temperature was constant. But here the temperature is slowly there.
This was in a paper with Sandeep.
It's in the paper. Now, arbitrary.
Yeah.
I should have paid more attention. I wouldn't understand it.
Okay, thank you.
Any other questions? I had a sort of slightly tangential question perhaps. So in this theory of quantum channels and so on, directive entity provides bounds like in the monotonicity of that entity coming. But for general quantum channels, right?
Yeah.
So could you imagine using this technology to derive some bounds, effective action perhaps coming to that?
Well, okay, so in some sense, yes, because that was the ideal principle when we derived the effective actions. Right? Statement I made about this topological symmetries, the work we did with the holography, which was we wanted to recover the scan law from quantum language. That's really the statement of the monotonicity of the relativity. In some sense, yes, but I've never managed to dot all the lines.
So just as a non-expert, just to understand, to come back to your original motivations, so you have these hydrodynamic modes, you can anticipate. It takes a long time, so going to accumulate, and is there a signal of that in the fluctuations? The fluctuations build up slowly again.
Yeah, they behave
Very slowly.
I wrote down the KMS relationship, time scale for fluctuations are also set by time scale in the three diagrams.
This one very expressed by the three constants.
So if there are no further questions, let's.
Okay, great talk. Thanks a lot.